Okay, so today I want to talk about Fourier series. Okay, so maybe I'm going to start with some generalities and then recall some things. So generalities. Let me say what the objective is first. Objective. So to understand Fourier series. And this in general goes with expanding into bases of orthogonal functions again. So we're wanting to take a function and then write it as a linear combination of a bunch of other functions. This is section 12.2, and then section 12.3. So let me just say what a Fourier series is. Okay, so a Fourier series, I'll just start with that, and then I'm going to say some generalities. Okay, so a Fourier series or a trigonometric series of a function f of x on an interval say minus p to p is the following. Is an expression of f of x as a sum like this and then we're going to express it as a sum. So an cosine 2 pi x over p plus bn sine 2 pi x over p. Okay, like this. So is this expression. So you're writing it as so we write this. Sorry, not 2 pi x. We just do pi x over p. I guess you could write it like this: 2 pi x over 2p. Maybe that's another way of writing it. Because 2p is the length of this interval here, right? And then 2 pi x would be to normalize it so that 0 to 1 would have so that would be periodic for 0 to 1. Okay, all right. So this is what a Fourier series is, and we can figure out. So one of the goals is to figure out what these coefficients are. All right, and I guess I can just get straight to the point of what the coefficients are, and then maybe we can derive what they are. And so notice that this is an over 2 here, and I'm going to explain that in a bit. Okay, so the formulas are the following. So A0 is this. Okay, AN. So this is, you take the inner product. Okay, and then BN here, minus P to P. It's like this. Okay, so we can get the coefficients like this, and let me talk about a little bit about where this comes from. So, and let me say this is a real Fourier series. Okay, so we're going to have a complex Fourier series in a bit, and this is going to be distinct from, well, it's going to be a little bit distinct, but we're going to have a different basis. All right, so let me talk about generalities for a second, and then we'll derive this, and then we'll do an example. All right, so that's the plan. So, okay, so this is like, so this is supposed to, so when I talk about generalities, I'm not like doing that just to be like weird, right? The reason I'm talking about generalities is to kind of explain how this fits into the whole scheme of expanding things in terms of functions, okay? Then I'm going to derive the formulas, and then I'm going to do examples. Okay, so this is the plan. All right. All right. So okay, so we talked about inner product spaces, and what I want to say is that these guys here. So one. So let me write this. So on the interval, minus p to p, the functions here, the constant function 1, cosine pi x over p, cosine 2 pi x, or yeah, 2 pi x over p. And I guess I could repeat, so then I could have sine pi x over p, cosine 2 pi x over p, like so, right? Form an orthogonal system. Okay, we've seen in other orthogonal systems, right? On different intervals. Namely, we have two examples that we've talked about. Okay, let me say, right? On the interval 0, 1, the first system that we saw, which came from the vibrating string problem, was this sine n pi x over 2. Or sine n pi x, like this, right? The second system, which is kind of a special case of this one, except for the interval here is a little changed. It's sine 2 pi. So let me write it like this. So n is an element of the natural numbers. Okay. And then we had the following system. The second system consisted of 1 sine 2 pi x, sine 3 pi x, so on and so forth. And then we had cosine 2 pi x, cosine 3 pi x, and so on and so forth. So here, note that there's here they're multiples of pi x, so it's not a full period, right? So these things contain like half waves, these, right? And then these ones only contain full periods, like this, okay? Okay, so we saw two systems on here. So there's a bunch of different orthogonal systems that we can construct. Okay, they're not unique. I just wanted to warn you that sometimes what the book calls Fourier sine series is not exactly the basis. Okay. All right. Well, and I haven't really told you what a basis is. Okay. So these are orthogonal systems. So these are collections of orthogonal functions. Okay. These things have so depending on the inner product you have. So on this interval, it's the integral from minus p to p, and then you multiply the two functions together. And on this interval, 0 to 1, you take the integral from 0 to 1, and you multiply two functions together. Okay? So these systems have the property that they are complete. Okay? And what does this mean? So definition. Okay? So a collection of vectors in an inner product. Let's give them a name. Let's say phi n in an inner product space. V, let's call this H actually. H is complete if and only if one of two things hold. So if and only if, let's say, so functions, or let's say elements, so there's two things I can say. I can say that you can write functions as a, let's say orthogonal vectors is complete if and only if one, let's say this. Let's do it like this. If V in H has the property that this is what the book uses. 0 for all n, then V is 0 as an element of H. Okay, so that is it's the 0 vector. Okay. So there's an equivalent way of saying this. It's something we won't show. But it's true, right? We can say that that the phi n are what are called dense. This means that any vector can be approximated arbitrarily well. Linear combinations of this set here. Okay, so that means essentially that essentially you can write them as a series. So you can write any v as a series in these phi n's. Okay. All right, and so okay, so let me give you a definition now, just so you guys can see this word. And if you hear this word from now on, you'll know that people are talking about these bases. Okay, so so a Hilbert space is a complete inner product space. So it's a vector space with an inner product, and it's complete. And by complete, let me just explain what complete means. So a vector space, an inner product space, is complete if it has a complete orthonormal or orthogonal system of vectors. Okay, meaning that you can find essentially a basis like this where you can, so the idea, so you can write H as okay. So it's like the infinite dimensional version of like having a bunch of orthogonal vectors and inner products. So when people talk about Hilbert spaces, that's what they mean. Okay. So the book uses this definition. Let me let you guys catch up for a second. Mm-hmm. Hilbert Space, Hilbert has like so many things named after him. So the question was, does the Hilbert Space have anything to do with the Hilbert Hotel? The Hilbert Hotel has to do with producing, I guess, playing with infinite sets. So the Hilbert Hotel says if you have an infinite number of people in a hotel, you can always make room for one more by having the people slide over. This doesn't really have to do with that, no. So this has to do with these inner product spaces. I think there was a story where like Hilbert, so he was at a conference and people were like, so you take this Hilbert space, blah, 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 and then he had to ask the question what a Hilbert space was. So like, because people tend to name things after people. Yeah, so this is actually really common. Like, people have things, so one time, there's a guy named Cartier, and he has a Cartier operator. And we're like, oh, well, you take the Cartier operator and you do this. And he's like, what's a Cartier operator? Well, I guess he knew what well, it depends, I guess. I don't know. It's kind of funny because, like, things are named after people sometimes. They don't really know what they mean. I don't know. I think that's funny. OK. So anyway, this is what a Hilbert space is. And we've actually been talking about Hilbert spaces. And you guys have been working with Hilbert spaces, OK, secretly. OK? All right. And so, all right, so let's talk about how to get the formula. So recall, OK, so the idea, OK, so in our examples, the Hilbert space is what we call H, which is L2 of 0, 1, right? And the two orthogonal systems wrote down are two examples of bases. Okay, so what is this thing? L2 is maybe not so important, but these are functions on the interval 0 to 1, where this integral, this thing makes sense. And in particular, you can like take continuous functions, right? And then you can take like limits of them, right? So, so that you can break them up and stuff. And so to get into the weeds of all like why bases exist and all these things like this, and so like if you have an arbitrary Hilbert space, like how do you prove things about convergence and things like this, you'd have to take another class, which is the analysis class. Okay, and you can take lots and lots of classes on these things. So we could get very into the weeds if we talk about that too much. All right, but I just want to tell you that that's what these things are, and when people talk about them, that's what they mean. All right, so let's talk about that formula. Okay, so so where does that Fourier series formula come from? So we're going to derive the formula. So recall that if H is a Hilbert space, with basis phi n, like this, so now I can say, oh, this makes sense. We can write H, so H and H as, well, H is the sum of A n phi n, 1 to infinity, for let's say A n in elements. So we're doing real Hilbert spaces. You can do them over the complex numbers too. We'll do this for right now. Okay, and then what did we do? So we recall that we had an was f phi n over phi n phi n. Okay, so this is an orthogonal basis. So this is so let me say orthogonal. Okay, so these things need to have inner product 0 with each other. Okay, so we have this thing. Okay, so the formula for Fourier series. Okay, so the formula. So this was done by Euler. Okay, he didn't use the word Hilbert space, but he just wrote down the formula and didn't care about whether or not things converged and things like this. The formula for Fourier series is a special case. Okay, so phi n here. Okay, so I should say, let's say phi k. Okay, so this was the set 1. Let's say Fourier series on the interval is okay. So here, let's do phi k. So this is the set where I'm going to write down this. So we have this basis. Cosine pi x over 2, say pi x over p, cosine 2 pi x over p. Okay, and then we have, this keeps going, and then we also have sine pi x over p, sine 2 pi x over p, dot, 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 like so. Okay? So here, okay, so then, so a function on minus p to p, or an element of L2 minus p to p, right, is written as, well, let's write some coefficients, okay? It's written as something times 1 plus a1 times cosine. Let's call this, let me call these alphas, actually. Alpha, because remember there was this weird coefficient where I had an a0 over 2. And I'm going to explain that. Okay? So cosine of pi x over p plus alpha 2 cosine 2 pi x over p plus dot 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 plus, and let's call this beta 1 sine pi x over p plus beta 2 sine 2 pi x over p plus dot dot dot. Okay? So here I just wrote the same thing that we wrote here, except for I used an n here, right? Okay, so all I'm saying is that you can write down a sequence of these functions here. This n doesn't necessarily correspond to these n's or k's here. Okay, does that make sense? So there's some sort of, it's just the fact that I have a list of them, right? Okay. Okay, and here, alpha 0, well, this is the inner product of f with 1 over 1, 1. Alpha 1 is equal to f with cosine pi x over p. And then we take this thing, cosine pi x over p. Alpha 2 is f with cosine pi 2 pi x over p. And then we have cosine 2 pi x over p, cosine 2 pi x over p, like so. And then this continues. Okay, it continues, dot, dot, dot. You know, alpha n is f, so pi n x over p. Okay, and then beta 1, okay, I guess this could continue. Okay, beta 1. All right, you guys don't need to copy this all down if you want to be fast. Sorry, pi x over, like this, sorry. Sine. All right, and then it keeps going. So you get to beta n. Sine okay, I guess you could keep going. Okay, so like these formulas here, we get formulas for the coefficients of these alpha. So we get the formulas for these alphas, and we get the formulas for the betas here, and those will give us these things. And eventually, this is going to turn into our formula for the Fourier series. All right, so let me just continue this. All right. So it turns out. So things we need. All right. So cosine pi x over p. Cosine pi. Let's do pi nx over p. Pi nx over p. So this thing here is the integral from minus p to p. Pi nx over p squared, and this is equal to p. So this is a fact. All right. Also, same thing. This is for n greater than or equal to 1. Sine pi nx over p sine pi nx over p. This is also equal to p. Okay. The one thing that we need to worry about is the first coefficient, right? So it turns out that this thing, minus p to p of dx, so this is 2p. Okay? So this tells us that, okay, so now we can write out what this formula is using the expression here. So alpha 0 plus, let's say, the sum of alpha n over p like this. Okay, so this is equal to alpha 0 was this integral here. So it's the integral, okay, so it's the integral of 1 over, so it's 1 over 2p. So this is this thing over 2p, 0 to, or minus p to p of f of x dx. Okay, so this is the first coefficient. So this thing was a0 over 2 plus, okay, and let's write the sum out. Alpha n, so alpha n was this thing over p, right? And then we had the, let's write it like this. 1 over p times the integral from minus p to p. Now I'm going to do the inner product here, right? F of x n pi x over p. So we have this coefficient. Let me just write this out because we have it all over there. Okay, 1 over p. So we have this first term plus, and then we have another integral, 1 over p. So 1 over p is the denominator. That's what this thing is. These two things here. The integral from minus p to p of f of x n, or n pi x over p, this coefficient. And then we have sine n pi x over p, like this. Okay, and then we have this big parentheses here. So this term here is the an, or this is the bn, what we called bn. And this term here is what we called an. Okay? So that's how to derive the coefficients for, so like you get the extra 2 because here it turns out that the inner product of 1 with itself is different from the inner product of cosine with itself and sine with itself. And that's why you get this 1 over 2 here in the formula. So it's really like 1/2. Okay, so I guess you guys kind of got to see with the picture where the coefficients come from. All right. So next time I'm going to apply this in an example. So we don't have a quiz next time. We'll have maybe the quiz time after that, or maybe one more after that. Okay. So like we're going to push up. There's no quiz next time. So maybe on Monday, probably on Wednesday. All right. So if you have questions, I have office hours right now. All right.